In this episode of Remote Linear Algebra, we will be looking at the method of using normal equations to find an orthogonal projection of a vector that does not lie in the span of two other vectors. Here we have a plane in R3 spanned by the vector 283 and 114. These two vectors are independent, thus they span a plane and not a line, but they're not perpendicular to each other. They're not orthogonal. But the method of normal equations allows us to work with the original vectors and not have to find an orthogonal basis first in order to find an orthogonal projection. We're going to try to approximate the vector -2, 1, 6 that does not lie in this plane. That's the green vector here. So the green vector does not lie in the plane spanned by 114 and 283. They're represented by the blue and the red vectors. So the method has us use this equation, A transpose times A times X equals A transpose times Y. A is built from the vectors that form the original span space. So for our example here, matrix A is going to contain 114 and 283. Y is what you're trying to approximate. I'm wanting to try to approach -2, 1, 6 as closely as possible in this plane. And then X is a solution to this problem that we have. I mean, you can kind of think of it as that it's the solution to trying to get A to map something to Y. But we know we're not going to get exactly Y, we're going to get an approximation. So building our normal equations for our system that we have here, one of the vectors in the original span was 114, the other was 283. That forms matrix A. The transpose turns rows into columns and vice versa. So 1, 2, which was a row, is now a column. 1, 8 is now a column. 4, 3 is now a column. This is a 3 by 2, or sorry, this is a 2 by 3, 2 rows, 3 columns. This is a 3 by 2, 3 rows, 2 columns. When you multiply a 2 by 3 by a 3 by 2, you get a 2 by 2. Notice a transpose times the matrix that created the transpose, you're always going to get a square matrix. In this case, when I multiply these two together, 1 times 1 plus 1 times 1 plus 4 times 4 gives me 18. And then 2 times 1 plus 1 times 8 plus 4 times 3 gives me 22. 2 times 1 plus 8 times 1 plus 4 times 3 also gives me 22. And 2 times 2 plus 8 times 8 plus 3 times 3 gives me 77. On this side, we're multiplying A transpose by the vector that we are trying to approximate. So -2, 1, 6 is a vector that does not fall in the plane that we are trying to approximate. So -2 plus 1 plus 24 gives me 23. 2 times -2 plus 8 times 1 plus 3 times 6 gives me 22. Now we're trying to solve for X. So X will be equivalent to the inverse of this matrix multiplied on both sides. So when I multiply this side by the inverse of this 2 by 2, I will get X, and I need to do the same thing on the other side of the equal sign. The inverse of this matrix turns out to be this 2 by 2, 7 over 82, -1 over 41, -1 over 41, and 9 over 451. I know the numbers are not quite as clean as the ones we got over there. If I multiply these two together, I get some other kind of messy fractions. I get 117 over 82 and -5 over 41. That is my solution to this equation. Now what the solution is, again, it's creating a linear combination for me that is going to be approximating y in my span. If y was in the span, if y was in the plane, then there would be a linear combination of these two vectors that created the vector in the plane. But it's not in the plane, so what this is, these are the scalars for a linear combination that gives us the closest approximation. So 117/82 is going to be the scalar multiplying 114. Negative 5/41 is going to be the scalar multiplying 283. And then I create this linear combination of my two original vectors, and I get the vector 97/82, 37/82, 219/41. And by the way, that's approximately 1.18, 0.45 for y, 5.34 for z, and we were trying to approximate -216. So in this plane, that is the closest point in the plane to the terminal point of this vector. Now you can apply this idea to any size system in any dimension. So we could have another situation where we have three vectors that are in the fourth dimension in R4, and they span a three-dimensional space in R4, and this vector is not in that space. You could test that by trying to make a linear combination of these and getting it to equal this vector, and if you set up that system of equations, you'll see that there is no solution. You'll get an inconsistency in that system. So using the normal equations, my A matrix is -1, 3, 1, 1 is the first column, 6, -8, -2, -4 is the second column, 6, 3, 6, -3 is the third column. And then my normal equations have me take A transpose times A. This is what we're trying to solve for. Then A, that will equal A transpose, and then this is the vector that we are trying to approximate. I'm trying to approximate this vector in the span made by these three vectors. If you multiply A transpose by A, this is the matrix that you get: 12, -36, 6, -36, 120, 12, 6, 12, 90. Again, I'm trying to solve for x. And if I multiply A transpose by the vector we're trying to approximate, this is a 3 by 4, multiplying a 4 by 1, I get a 3 by 1 of 23, -32, 153. X then will be the inverse of this matrix, multiplying this 3 by 1. And if I follow through with that, I get this as the inverse matrix, and this 3 by 3 multiplying my 3 by 1 gives me this 3 by 1, -43/2, -57/8, and 49/12. And again, what these are the scalars that would form a linear combination of the original vectors, and we're trying to get a linear combination to equal the original y, but y doesn't fall in the span, and so what we get instead is a best approximation to y. So if you take -43/2 times -1, and then you add it to -57/8 times 6, and then add it to 49/12 times 6, you get 3.25. And you could do that for the other three components. So -43/2 times 3, added to -57/8 times -8, added to 49/12 times 3, gives us the 4.75. So in the three-dimensional space in R4 that is spanned by these original vectors, the closest point in that space to 3, 5, 17, negative 6 is this point. And you can actually put all of this information conveniently in your calculator. You have to be a little bit careful typing everything in and so forth. But if you take your original normal equations, okay, so here's our original normal equation, A transpose times A times X equals A transpose times Y. You initially solve for X, and then you use those values as scalars of a linear combination to actually get your approximating vector. So first you have to get X. So in terms of calculator usage, you might want to try this somewhat shortcut, but again, you have to be careful typing everything in. If you solve both sides of those normal equations for X, then X by itself is equal to the inverse of A transpose times A multiplied by A transpose and then multiplied by Y, the vector that you were trying to approximate. I know it seems like you should maybe first multiply both sides of the equation by A transpose and, or sorry, by the inverse of A transpose and then multiply by the inverse of A. However, your A might not be square. It wasn't in this case. It was not a square matrix. So I cannot find inverses for non-square matrices. That's why first you do have to multiply A transpose by A, and then you take the inverse and then follow through. So on our calculator here, I have in A, I have our original matrix A, negative 1, 3, 1, 1 is the first column, 6, negative 8, negative 2, negative 4 is the second column, 6, 3, 6, negative 3 is the third column. And then in B, I have the vector that we were trying to approximate. We're trying to approximate 3, 5, 17, negative 6. So now I'm going to carefully follow my rule here. So I'm going to put parentheses, I'm going to type in what I have here. So A, and then how you get transpose is you go into matrix, head over to math. The second program is transpose. And then we're going to multiply by matrix A, and I want the inverse. To get the inverse, you use the reciprocal button. The calculator knows you're working with matrices when you press that. And then I'm going to multiply by matrix A transpose again, so I have to go in and tell it transpose. And then lastly, we're going to multiply by, I put the vector we're trying to approximate in B, and those numbers look a little messy, but if I hit math and then fraction, the first program, so I'm hitting enter right now, it converts the decimals into the fractions, and those are the same fractions that we had earlier. All right, so again, if you're careful, you can type all of this in your calculator and get your scalars for your linear combination kind of in one big step. And once again, what we found by using our normal equations is represented by this yellow vector. Notice it's immediately underneath the green vector with respect to the plane. It's like the shadow cast by the green vector in the plane. And so the tip of the yellow vector is perpendicular in the closest point to the tip of the green vector in this plane. Again, the yellow vector has x coordinate 97 over 82, y coordinate 37 over 82, and z coordinate 219 over 41.